So in the previous lecture, we have discussed an example where we looked at the application of direct product in solving energy elements, right? So in this one, we'll look at one more application of direct product where we'll be looking at something called as spectral transition probabilities. Spectral transition probability. So what is it? What is the meaning of this term? Let us first try to understand that. So if we have two energy levels, if we are trying to perform spectroscopy and we have two energy levels, let's say E1 and E2, and then there is energy difference between this, which is defined by nu. So the energy corresponding to h nu will be able to carry out the transition from E1 to E2, right? And whether this transition will take place or not will be defined by the selection rules, right? So selection rules will tell you this. You must have learned in spectroscopy that whether the transition will be possible or not. So let's say, how does the selection rule come actually? So the intensity will of this transition will be directly proportional to psi 1 mu psi 2 d tau. Okay, so where psi 1 defines the state for the state 1 and psi 2 defines the state, the excited state, right? And mu, what is mu? So mu is called as transition moment operator. So which can take different forms, as in it can correspond to mu can correspond to changes in electric or magnetic dipole, polarizability tensor, etc. So depending on what type of spectroscopy we are using. So let's say in this case we are considering electric dipole allowed transitions. Okay, so electric dipole allowed transitions. So what is the meaning of this? That means the charge distribution in ground state and excited state corresponds to or differ in a manner which is similar to a electric dipole. So here charge distribution between the state 1 and state 2, or that is the ground state and excited state, forms like a electric dipole over here. So if this electric dipole can now interact with the oscillating electric field vector of the electromagnetic radiation, and then that interaction leads to either absorption of energy by the system or release of energy by the system, then we say that there is a transition which has been carried out, right? There is a change in the dipole moment that has been carried out because of the applied frequency, right? So now let's say that what is the form of mu? So mu can be written as summation ei xi plus summation ei yi summation ei zi, right? And this will be summation over all I. Actually summation can be taken common here. Okay, so what is ei? Ei is charge on ith particle. and xi, yi, zi are the coordinates of the particle. Right? So these are the coordinates and charge. So now that means if I want to write the intensity factor again, so I can say that the intensity in x is proportional to integration of psi I x psi j, or you can write 1 2 here, d tau. Similarly, intensity along y will be proportional to psi I y psi j d tau, and intensity along z will be similarly proportional to psi I z psi j d tau. Now I will not be equal to 0 if any of this ix, iy or iz is not equal to 0, right? So you can take, if ix is not equal to 0, then also the total intensity will not be equal to 0, or if iy is not equal to 0, total intensity will not be equal to 0, and so on, right? So what we need to calculate, we need to calculate individual contribution of intensities, and if any one of them is not equal to 0, we will say that the spectral transition will happen, otherwise the spectral transition will be forbidden. And that's how you define the selection rules, whether these two states will have transition from one state to another or not. Given the particular frequency, the spectra will be, transition will be allowed, otherwise it will be disallowed, right? So now let's say when this integration will be non-zero, the integration will be non-zero when the direct product of the psi I x psi j, I mean the corresponding IR representations, will contain totally symmetric representation. So Ix will not be equal 0 if psi I x psi j corresponds to IR representations whose direct product contains TSR, right? And similarly, we can say for IY and IZ. Now there is interesting thing that we have x, one of the function we know that it's a unit vector along x, right? X can be treated as unit vector, y is unit vector along y, z is unit vector along z, right? So we already know, if we refer to any character table, we already know the IR representation corresponding to x, right? And similarly corresponding to y. So that means we can reduce this condition to, if psi I and psi j correspond to IR representations whose direct product contains an IR which has x as the basis. Because if it will have x as the basis, that would mean that the triple direct product will contain A1, right? Similarly for y and z will follow, right? To see, right? So we can now write a statement that an electric dipole mm, transition will be allowed with X, Y, or Z polarization. So why X, Y, or Z polarization? Because this is the polarity of the radiation which is applied, right? If the direct product of the representations of the two states which are psi I, psi j, and psi I, two states concerned, is or contains it's the irreducible representation to which X, Y, or Z belongs, right? So if psi I and psi j together will form a direct product which either corresponds to an IR representation containing X or contains an IR representation with basis X, Y, or Z, then this integration will survive, and then we will say that the integration is not equal to 0, and then thus the spectral transition will happen. Otherwise, the spectral transition will be forbidden. So now let's look at an example. We'll try to see if we can solve it. So let me frame the question first. So it's a solved example in cotton, but let's see how to do this. So let's say it's a metal. We are talking about metal-based electronic transition of MO2 Cl8 minus, right? Yeah, Cl8 4 minus species. So first of all, the structure of the molecule is given, so which is MO, and this will be Cl, 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 and then you have another one. It's like a sandwich. So we have two planar molecules, and then there is a metal-metal bond over here in between. Okay, and the whole thing has 4 negative charges. So let's say if you want to draw the XY coordinates, we can will be the z-axis will be passing through this, right? And we can say that our x will be passing through one of this, so we can draw x like this, and y will be passing through another Cl bond, so we can say our y will be like this, right? So try to imagine this. Let me draw it like this in different color, right? It's too bad. Okay, right? So this is the molecule which is not square planar, but you can say that it's a square parallelopiped or square prism also you can say, right? And we can also say that the point group will be like square planar, so it will be d4h, right? Because there is a symmetry sigma h over there passing through the metal bond, right? Now, so now they say that this is the molecule, and HOMO is the highest or occupied molecular orbital is delta orbital, which is basically composed of dxy orbital, and it takes the shape like something like this. So this is the delta orbital, and this is given in the question. And the lowest unoccupied molecular orbital, which is delta star, it's also composed of dxy, but now there is a change in symmetry. So we have this one is same, whereas here there is a change of negative and positives. So you have plus and minus, right? So you can see that these two are different. So this whole thing constitutes delta, and this whole thing constitutes delta star. So these are two dxy orbitals which are kept on top of each other, and in this one there is a phase difference between the two, and that's how this is called as delta star, and this is with same phase, so this is delta. Now I will write down the question which this is asking. So we need to see whether if delta to delta star, that is HOMO to LUMO transition, so HOMO to LUMO is electric dipole allowed or not. This is the question they are asking. So that means what we need to do is we need to set up a integration where we need to see whether psi d, psi delta, x, y, z, and psi delta star d tau. Now this integration, whether this is equal to 0 or is not equal to 0, right? We have to identify this. So what do you do in such a case? What you have to do is you have to first identify what is the basis for these orbitals under d4h point group. Okay, so d4h point group, let me write down the symmetry elements. So this will be 2c4, c2, 2c2 prime, 2c2 double prime, I, s4, e2, sigma h, 2 sigma v, 2 sigma t, right? Now for delta and for delta star, what we need to do is we need to carry out these operations and see what is the fate of this delta orbital and delta star orbital, and depending on that we'll need to give the characters over here. Okay, so I would suggest you to do it. I'm not going to show it how to do it here. So E will be 1 for both. So if you do a C4 operation, so if I do a C4 operation, plus goes to minus, the negative lobe goes towards the positive lobe and positive lobe goes to the negative lobe, and this happens for all of them. So that means all the positive signs go to negative, all the negative signs becomes positive, right? So this would mean that you have the character under C4 as -1 for both the orbitals, right? Similarly, if you do a C2, the positive is exchanged with positive because opposite, it's a 180-degree rotation now along z axis. So positive goes to positive, negatives go to negative, and so on. So C2 character is +1. So in the same way, you can carry out all these and find out the character. So I will just note down the characters from my notes, and these are 1, -1, -1, 1, 1, -1, -1, 1, 1, -1, 1, 1, -1, -1. So remember that you have to take both the orbitals together and orient it along the coordinate system as they are, because it's a dxy orbital. And once you do that, you should be able to carry out all these operations. So try to do it yourself so that you know how to find this out. So once you do that and you find out what is my representation corresponding to delta and delta star, I can now compare it with the standard character table of D4H and find out that my delta is actually, so one of them is B1G and the other one is B2U. Okay, so now I have find out the IR representation corresponding to the bases delta and delta star. Now for X, Y and Z, Z corresponds as A2U. So this can be read from the character table. So you know the unit vector transformations are written in this area, and then what is the IR representation corresponding to Z, you can find out. And XY is jointly forming the basis for EU representation. Okay, so now what you have to do is, now the problem is simplified to finding the direct product between B1G, EU and B2U, that is 1 for X and Y, and for Z you have to do that B1G, A2U and B2U. So as it turns out, if you do this calculation, all you have to do is you have to multiply the corresponding characters and traces and find out what is the IR representation here, whether it contains a totally symmetric representation or not. So as a matter of fact, this one contains A1G plus something else it may contain, but one of the representation is totally symmetric representation, right? So if it contains totally symmetric, that means we can make a statement now that delta to delta star transition is allowed, or you can say electric dipole allowed. Because that is the form of mu which we have taken here. Electric dipole allowed with Z polarization, because we found TSR only in Z integral, right? The other integral, which was XY integral, we did not find A1G. So then we can say that and forbidden for radiation with its electric vector in the XY plane, right? So look at the power of this method. So you now know not only the selection rule, whether the transition will be allowed or not, but you also know with what polarization the particular transition will be allowed. So you you don't need to actually throw in the light with all polarization. So if you just throw in the light with Z polarization, the electric dipole transition will be allowed, because XY light is not being used here, right? So you not only come to know whether a transition is allowed or disallowed, but you also get the details of which polarization the transition is allowed. So with this, we finish the direct product application, and in next class we'll be looking at symmetry adapted linear combination. So we'll be looking at the chemical bonding and all. All right, that is all for today.